A bar is an SVG rectangle. First, D3 selects the SVG. Append creates one rect inside it. X and Y place the rectangle, while width and height make it visible. That is enough to put a real mark on screen. No data, join, scale, or axis is required yet. Append returns a D3 selection containing the new rectangle, and we saved that selection as bar. Calling iter on bar changes the element that already exists, still controls its paint, so the rectangle turns steel blue as this single line runs. This selection then modification pattern is fundamental. Obtain a set of elements, then describe the attributes those elements should have. The next iter call replaces height on the same rectangle. Nothing is appended, and the x position, y position, width, and fill remain unchanged. This is the first update. One property changes, so one visible property responds. Now we repeat the rectangle with data. Each object has a name for identity and a value for magnitude. Select all describes the rectangles we want. Data binds the four objects, and the key callback identifies each one by name. Join creates one missing rect per object. The temporary X formula spreads them apart, while Y, width, and height give us four small visible marks immediately. They are rough, but the data join is already real. An attribute can receive a callback instead of a fixed number. D3 invokes that callback once for every bound object and passes the current datum as D. The Y callback moves the top upward by 10 pixels per value unit. The height callback uses the same multiplier, so every bar still ends at the baseline. This is deliberately simple pixel math. It makes the data relationship visible before we replace the hard-coded conversion with a scale. The index formula works for 4 bars, but it mixes layout arithmetic into the drawing rule. Scale band owns that job. Its domain is the ordered list of category names. Its range is the horizontal chart space, and padding reserves a gap around every slot. Calling X with a name returns that category's position. Bandwidth returns the usable width inside the same slot. When these lines run, position and width move together into one consistent layout. The 10-pixel multiplier has the same limitation, so we replace it with a linear scale. The domain states the data interval 0 through 20. The range runs from the baseline at 230 pixels to the top at 20. That reversal is intentional because SVG Y coordinates increase downward. Calling Y with a value returns the top edge. Baseline minus that coordinate returns the bar height. The chart can now change size or domain without rewriting the callbacks. The x-axis is generated from the scale we already use. A group element holds the axis output and moves to the chart baseline. Axis bottom reads X's domain for the labels and its band positions for their centers. We do not calculate tick coordinates a second time. The bars and their labels align because both are consumers of the same scale. The y-axis repeats the same pattern with the linear scale. Its group moves into the reserved left margin. Axis left chooses readable values from y's domain and maps every tick through y's range. 0 lands at the baseline, and larger numbers climb upward. Because the axis and bar callbacks call the same converter, changing the domain or chart height keeps their geometry synchronized. Only b's value changes from 18 to 6. Its name is unchanged, so the key function matches the new b object to the existing b rectangle. The y and height callbacks run with the new value, moving its top down and shortening its height. A, C, and D resolve to the geometry they already had. The chart changes because the data changed. The rendering rule does not need a special case for B. Now the objects move into D, B, A, C order. Mapping their names rebuilds the band domain in that order, so X assigns new horizontal slots. The key still says that D is D and A is A, independent of array position. D3 can therefore reuse each rectangle while its X attribute changes. This is why a stable key matters once a collection can be reordered. The final data edit removes C and adds E. During the join, D, B, and A match existing rectangles by name. C has no matching datum, so its rectangle exits. E has no matching element, so join creates a new rectangle, and the same attribute callbacks give it position, size, and color. Enter, update, and exit are not three separate drawing programs. They are three outcomes of comparing keyed data with the current elements. The complete pattern grew from visible steps. Append showed that a bar is one rectangle. Data and join repeated that mark for object-shaped data. Attribute callbacks connected each rectangle to its datum. Scale band replaced horizontal index math, and scale linear replaced vertical pixel math. Both axes read those same scales. The name key preserved identity through value changes, reordering, removal, and entry. Each abstraction arrived only after the simpler version had already produced a result.